This lesson is the definite integral, the fundamental theorem of calculus. In an earlier lesson, we stated the fundamental theorem of calculus. We want to restate it here. If f of x is a continuous function where x is between a and b, then the integral of f of x dx is equal to some antiderivative, which we're designating as capital F of x plus c. Now that is your indefinite integral that we've been using all along. And now we're adding that the integral of f of x dx from a to b is equal to f of b minus f of a, where f is this antiderivative of f, as explained here. Now, word of caution before we go too far into the lesson. When you find the definite integral, it does not mean you're finding necessarily the area under the graph of the function. It could be, but it's not necessarily is the area under the graph of the function. It is only the area if the function indeed is above the x-axis. I want to make that point as we're working problems here, because sometimes we'll get a negative answer when we do the definite integral. And we don't want you to think that that the area is negative. We'll explain that in a later lesson and say no more about it here. This lecture is meant to acquaint you with the concept of the definite integral. That is, to familiarize you with this fundamental theorem of calculus. And in doing so, we hope to give you an opportunity to practice some of your antiderivative formulas that you learned earlier. So let's look at an example. Example 1 asks you, integrate 4 dx from -3 to 2. Well, the integral of 4 dx is 4x. Okay, that's the antiderivative. And if we were just finding the indefinite integral and we had no values listed as the between, in this case, -3 and 2, then the answer would be 4x plus c. But this is not, this is just 4x. And this is, we're hanging out numbers here momentarily so that we don't do too much in one step. In other words, the antiderivative is 4x, and our limits are -3 to 2. Now, what the this is my capital F of x, and what the fundamental theorem says to do, evaluate this when you put in 2. So that's what we do. 4x when you put in 2 gives you 4 times 2, and 4x when you put in -3 gives you 4 times -3, and it's the difference of those two. In other words, it's 4 times 2 minus 4 times -3, and then you do the arithmetic, which we've done here, and you get an answer of 20. Okay, not really hard once you get into the rhythm, and that's all we really want to do in this lesson, is acquaint you with the rhythm of what we're doing when we have a problem like this. So let's go to example 2. This time our variable is t. We're doing this to let you know that the variable does not always have to be x. We see x so often, but let's do this one where t is our variable, and we want to find the integral of t squared minus 4 dt, where our limits are -1 to 1. So we find the antiderivative, which is t cubed over 3 minus 4t. Now that's your antiderivative, and here are our limits. And so what we're going to do is put 1 in the place of t, and when we do, we get 1/3 minus 4, and then we're going to put -1 in the place of t, and we get -1/3 plus 4, and then we're going to take the difference of these two, and this is going to give us the 2/3 minus 8, which is -22/3. Now, this is what we were saying earlier. This is just the answer. This is the definite integral. It is not the area, okay, because the area cannot be negative. But we're not going to say any more about that in this lesson. We'll save that for a later lesson when we emphasize area to a greater extent. Example 3. What we want to do here is recall what happens when you have 3 over x cubed. Well, the first thing you've got to do to integrate, you've got to write this is to the -3 power. Now we're going to add 1 to the exponent and divide by the new exponent. We're not showing every step here. This gives you -3 over 2x squared. Here are our limit values. So we'll put in 2 and we'll put in 1. Now we're pulling the -3/2 out. Now you don't have to. You can leave it with the 3/2 and do the arithmetic, but we're just choosing to pull that -3/2 out and treating this as -3/2 times 1 over x squared to do this. It doesn't matter. Either way, you're going to get 9/8 for your answer. So make sure you understand we're not showing every step at this point. If you need to show more steps yourself, please feel free to do so. Example 4, we want to review 1 over the square root of x, which you have to write before you find the antiderivative is x to the -1/2. And then we add 1 to -1/2, giving you +1/2, and dividing by 1/2 is like multiplied by 2 over 1. This is the antiderivative. We'll pull the 2 out. We'll put the 4 in, and which is the square root of 4. We'll put the 1 in, which is the square root of 1, and this gives us a net answer of 2. Check behind us with the arithmetic. Okay, so these are very good problems. Nothing tricky about them. It's just a matter of doing arithmetic. The only thing we're doing here basically is finding the antiderivative and then evaluating for the upper limit and the lower limit. It's all a matter of arithmetic once you find the antiderivative. So don't make more out of this than is. Example 5, we're looking at this so we won't forget that, yes, we're interested in trigonometry in this course, okay? This is calculus. It doesn't just involve algebraic functions, but it involves logarithmic functions, exponential functions, and trigonometric functions. So let's look at a trig function. The antiderivative of the sine is minus the cosine, and the antiderivative of 1 is x. And then we're going to evaluate it for pi over 2. So we'll put pi over 2 everywhere there's an x, and we'll put a 0 in everywhere there's an x. And of course, this 0 doesn't show up over here because 0 is 0. And then we have the cosine of pi over 2, which happens to be 0. And so this is going to give us just pi over 2. Cosine of 0 is 1, and minus of minus is a plus. And we put it all together, and we get pi over 2 plus 1. Again, we're not doing all the arithmetic and everything. So if you say, I'm not sure I see that, you can stop the lesson and check for yourself to see that this is indeed the answer you get. Now, all 5 of those are very doable problems. Now, when we get to example 6, we're having the antiderivative secant squared of t dt. This is not necessarily one of the formulas that we use often, okay? But we're want to put some of the lesser formulas into the lesson to let you know that you need to know those as well. The antiderivative of the secant squared is the tangent, and the upper limit is pi over 4, and the lower limit is pi over 6. So that'll be tangent of pi over 4 minus tangent of pi over 6. Tangent of pi over 4 is 1. The tangent of pi over 6 is 1 over the square root of 3, and that's a good answer right there. 1 minus 1 over the square root of 3, or we got a common denominator, and there's another way you could leave this answer. Now, this problem is much harder than the other 5 for a number of reasons. First of all, The antiderivative of secant squared is not as familiar to you maybe as some of the others. And also you have to know the tangent of pi over 4 and tangent of pi over 6, which might not readily roll off of your tongue type expression to say. So you may want to think about this one. This is a much harder problem. We admit to that fact than were the earlier 5. But take it for what it's worth, and we will move on. Example 7 is we have an exponential function where the antiderivative of e to the x is e to the x, and the antiderivative of 2x is 2x squared over 2, or just x squared, and we'll put in an upper value that's going to give us e squared plus 4 when you put in 2, and you're going to get, when you put in 0, this will be e to the 0, which is 1. Of course, 0 squared is 0, so we get this, and there's our final answer. That is a good problem. So of the first 7 problems, 6 of them should be fairly familiar to you because they all use our major antiderivative formulas. We had one exception to that rule that we spoke to earlier. Here's another one that's rather exception. This is the antiderivative of 1 over 1 plus x squared dx. That happens to be the inverse tangent of x. Not as familiar to you as some of the others. That's what it is. If you recall, we need to know that. So then we substitute 1 in. So that's the inverse tangent of 1 minus the inverse tangent of 0. Turns out that the inverse tangent of 1 is pi over 4. The inverse tangent of 0 is 0. And there is your answer. So that's another one that might give you a little more trouble. The trouble of this problem and the earlier one is that the integral of secant squared is not as well known, nor is the integral of 1 over 1 plus x squared as well known. And in addition, you have the trigonometry, which for some people adds a level of uncertainty when working a problem. So there we have problem number 8. Problem number 9, we want to include this one because this is our other important formula. The integral of 1 over x is ln of x from e to 1, and this is going to be ln of e minus ln of 1. Now ln of e is 1, okay? Talked about that earlier with logs, and the natural log of 1 is 0, so this answer is just 1. Now, let us take a minute to point something out to you. Let's suppose instead of 1 to e, this thing were 2 to 7. It would be done the same way, except that this would be ln of 7 minus ln of 2, which we don't know what that is. We can't, we just more or less would have to leave that answer. If this were 2 to 7, ln of 7, we'd have to leave it like that, minus ln of 2. But we're fortunate if we can go further with this because ln of e is 1 and ln of 1 is 0. Just want to make sure you understand that. And here's another minor formula. This is a very minor formula, but we thought we would round off the exercise by doing this. The integral of 2 to the x power is 2 to the x times 1 over ln of 2, or divided by ln of 2, from 5 to 2. So all we do is everywhere there's a x, we put a 5. We bring this out. See, this is like a constant. We bring this outside parentheses, and this will be 2 to the 5th minus 2 to the 4th. 2 squared, excuse me, 2 to the 5th minus 2 squared. 2 to the 5th is 32. 2 to the 2nd power is 4. 28 over ln of 2. So again, a harder problem. So that completes the problems we wanted to work. So if we go back quickly, 10, you're going to have to spend some time on. 8, you're going to have to spend some time thinking about, and 6. The rest of them are pretty standard problems, and we only say that to you so that you realize you're very much expected to do those. And it's not that you're not expected to do the remainder, it's just that they are a little more difficult, and we want to be honest with you about that fact. Now, let's talk about some properties of the definite integral. This first property says, if when you're doing a definite integral, these two numbers are the same, then the answer is always 0. And think about it. If you find the antiderivative and you put in a, you get an answer. And you put in a again, you get the same answer. And you subtract the two answers, gives you 0. Also, think about it. If you're finding the area under the curve, and if this graph is above the x-axis, it would be indeed area. If you find the area under from A to A, that's the area under a point. And there's no area under a point. A point has no length, width, or thickness, okay? So in all quarters, this is something you want to know. In fact, if you see that these two numbers are the same, you're free to automatically say 0. Okay? Now, property 2. If you have the integral from A to B, that answer is the opposite of the answer from B to A. In other words, if you switch the numbers, A to B, B to A, then the answer is the negative. And that should make sense to you as well, because what we do when we find the antiderivative, you put in B, you get an answer. You put an A in, you get an answer. In this case, you put in A, you get an answer, and you put in B, you subtract. So we're subtracting f of B minus f of A versus f of A minus f of B. So it makes sense that they're negatives. So basically, the same principle is 8 minus 5 is 3. 5 minus 8 is minus 3. Okay, same principle there. And we kind of explain it in a little more detail here. We want to read through that. This one is very important. If C is between A and B, okay, if C is between A and B, then the antiderivative from A to B is equal to the antiderivative from A to C plus the antiderivative from C to B. In other words, you break it up piecemeal. In other words, if you're going from A to B and you're going through C, you go from A to C, and then you go from C to B. You break up your trip into two parts. That's all we're doing. We're saying the function from A to B, if C is between A and B, is the same thing as A to C plus C to B. And you want to know that property. Some other things that we kind of alluded to earlier, none of these properties are all that hard, but we do want you to begin to think about them. We'll have a couple of exercises in a moment that will help you with that. But here we're making a statement of something we said earlier. If f is a function that's positive, always positive, greater than or equal to 0, that is above the x-axis, then when you integrate from A to B, that is, the answer is positive, and that is area, okay? If, on the other hand, though, the function is below the x-axis, and you evaluate from C to D, then that area is going to be negative. In other words, region under the x-axis, its area is negative. Now, it still is an area, but the negative indicates that the graph is predominantly beneath the x-axis. And then lastly, if you have two functions, f of x and g of x, and f of x is bigger than g of x, then the integral from f of x from A to B will be greater than the integral of g of x from A to B. Think of it in terms of area. Suppose you have a line, f of x equals, let's say, 10 from 2 to 4. And then you have another function, f of x is 6 from 2 to 4. Now, the area of the part, the 10, is going to be 10 times 2. That's the rectangle. Whereas the one from to 6 is 6 times 2. And so we're saying that if you have a region underneath another region, that the area under the upper region is bigger than the area of the region below it. It's so much common sense that we don't want to say any more about it. But you might want to read through these, not from a standpoint of being asked to list the properties of the definite integral, but you want to be able to use them. And some of those we're going to talk about now in a couple of exercises. Let's look at example 11. Suppose you're told that the integral of f of x from 0 to 2 is 3. And the integral of that same function from 2 to 5 is -1. And we ask you 3 questions. Now, this is given. We're not told what the function is. All we're told is we have some function. We have no clue what it is. We don't need to know what it is, but we're told that when you evaluate the function from 0 to 2, you get 3. And when you evaluate it from 2 to 5, you get -1. And what we want to know is, what's the answer when you evaluate it from 0 to 5? Well, here's what you've got to think. 0 to 2 plus 2 to 5 is 0 to 5. The transitive property we talked about on the previous page. 0 to 5 is 0 to 2 plus 2 to 5. So this is 3, this is -1, and the sum is 2. So that's the answer to this particular problem. Then we're asking part 2, what's the integral from 5 to 2? Well, the integral from 2 to 5 is -1. We've switched these numbers 5 to 2, they're reversed. So it's the opposite of -1, which is +1. And then we have one that's rather tricky. What's the integral of f of x minus 4 dx from 2 to 5? What we're going to do is we're going to break it up so that it's integral of f of x 2 to 5 and integral of -4 dx from 2 to 5. Now we know what this is. From 2 to 5, that is -1 from up here. This, can we integrate this? The integral of this is -4x. And we're doing it from 2 to 5, so it's -4. And we put in the 5, we get 5, and we put in the 2, we get that, and we take the difference and do the arithmetic. The thing about this set of problems is this. When you're given the function, you can kind of let your calculator sometimes help you do the work. Because you have the function, you have a calculator, and you can put the value into the function. We don't, with this, the calculator does not help you, and you should be aware of this. Textbooks, standardized tests like to ask questions like this because there's no computer or calculator that will help you. You just have to think through the problem. You're not doing really any work. But please notice, look at these and make sure these are kind of clear to you. If you have to, we're not doing all the thinking for you. We expect you to go back now and look at some of this and say, yes, that makes sense, okay? Some of you will pick it up quickly. Others of you will need to think a little bit more about it. But all of this information right here, plus the answers down here, hopefully will eventually make it clear to you. And then we have number 12. We're told another problem. The integral from 1 to 3 of some function, we don't know what it is 4. And the integral from 3 to 6 of that same function is 2. And we want to know the integral from 6 to 1. So this one is, all you got to do is, we want 6 to 1. Well, look, this is 1 to 3. This is 4. And 3 to 6 is 2. So 1 to 6 is 4 plus 2. Okay, 1 to 6. 1 to 3 is this. 3 to 6 is this. So 1 to 6 is 4 plus 2. This plus this. But we don't want 1 to 6. We want 6 to 1. So if this is 6, if 1 to 6 is 6, then 6 to 1 is what? -6. Now these should, as I said, these are thought problems. We're not doing any work. We're just thinking through the particular problem. So this is called the definite integral. It's called the definite integral because we're getting a definite answer, unlike the indefinite integrals where you get something plus c. See, we don't know what the plus c is, so we don't know the exact answer because we don't know what c is. So it's called the indefinite integral. In this case, our answer doesn't have a c in it. It's a numerical answer, and it's called the definite integral. So make sure you understand, and that the problems are meant to be so that by now you've picked up the basic tenet of the problem, which no matter what problem we give you, what you do is you take the problem, you find the antiderivative, which we know how to do that because we have all the antiderivative formulas, and then you put in the top limit and get an answer, put in the lower limit and get an answer, and take the difference of those two answers, and you're done. So don't overthink this, but this is something that's very important that you know how to do this, because this is going to follow you all the way through most of the remainder of the calculus lessons. So that will be all we're going to say about this topic.